Uma Desu is a leader, life coach, innovator, intelligence pioneer, publisher, trekker, webmaster, and angel investor. With over 25 years of experience in executive and managerial roles, he has made a significant impact in various fields. Currently, Uma Desu is the Chief Artificial Intelligence Officer at Gen AI Pioneer and the Chief Intelligence Officer of Intelli India LLP, a global company providing research, sales, and competitive intelligence services. He is also a certified prompt engineer and an expert in generative AI training, offering training in prompt engineering and AI tools. In addition to a strong focus on technology, he is the CEO of VV Creations, managing over 100 domains and portals. Uma Desu is an accomplished author of 4 fiction novels, with one being officially selected for the Indian Pavilion at the London Book Fair. The upcoming book, Gen AI, the trillion-dollar opportunity, is eagerly awaited and showcases Uma Desu's expertise in artificial intelligence. As a motivational speaker, he focuses on helping people overcome peer pressure and is the author of the books like The Peer and the Peer Pressure. He is also an angel investor supporting innovative projects, the CEO of Vihara Travels, promoting ancient temple tours, and a passionate trekker. With double master's degree and certifications as a life coach, he brings a perfect balance of knowledge, experience, and creativity. We are honored to have Uma Desu here with us today. Please join me in giving a warm welcome to our distinguished guest. Thank you, sir.
Thank you, ma'am. So, sir, can you make me the presenter?
Sure, sir. Sure.
So, good evening, everyone. Nice to be back at RBR College ATAL program. So today we are going to look at transformers. As for faculty, it's one of the most important things to learn, especially in this era of AI, because this AI revolution is being driven by one single white paper, Attention is All You Need, which came from Google DeepMind way back in 2017.
Sir, you are not audible. Sir, you are not audible.
Decades, but never we came close to processing text as much as we came close in transformers. See, transformers, again, if you look at the Indian philosophical thought, is again focusing on the questioning part, which Ramna's philosophy used to teach us, the oneness and the questioning part, and that's exactly what we look at. We don't look at just the words, we look at the meaning of the words, we look at the core behind it, and we never capture only a singular word, and that's what all other machines use it to do. Or RDP-based databases use it to do that, so it doesn't help us in that way. 1 minute. Connection. Sorry about the disturbance. Am I audible?
Yes, sir.
Hello?
You are audible. Yeah, yes, sir. You are audible.
Okay, oh,
Go
sure.
ahead. Go ahead.
Sorry about the disturbance. So transformers is the reason why we are in fact having this conversation because if there was no transformers, there would have been no AI revolution and wouldn't have been this having this conversation. So as educators, for us, it's very important for us to understand transformers and also to teach our generation, because our generation, the students, our students are totally placed away, very far away from the AI architectures which have been there from 2013. Now, if you look at AI architectures, we stopped at 2012. The AICTE syllabus doesn't go beyond that. So we only look at the neural networks. We don't even look at CNNs. If, somewhat triple guys at least learn reinforcement learning. We don't even learn that in our academic syllabus. So 2013 onwards, we had variational autoencoders, 2014 GANs and all. We don't learn any of these because all of them helped in analysis and data processing, especially text conversion. So the whole basis of the first pillar is obviously NLP, natural language processing. So were we able to split the sentence? Were we able to process text? Were we able to process data? So this was what determines all these issues for us. And what has happened is variational autoencoders came to us in 2013. Then we had CNNs and we had RNNs. So till CNNs and RNNs, we were still able to process text. We were able to go for sequential analysis of text. So today we'll look at why we have been focusing so much on transformers, why the earlier models didn't work, what were the earlier models. So if we look at both the history and the transformers, we'll also have some hands-on exercises today. So we'll also have some certifications done in transformers, since if you're learning transformers, it's best to be rewarded for that. Uh, it's best to be rewarded for that. So you need to be rewarded even for this transformers architecture. So we'll have an Google certification once we do this transformers study. And once we do this transformer study, we are also going to definitely have a look at NLP where it starts, because you don't understand NLP without understanding the basics of how data is being taken. See, for example, all of us are putting a simple line of text, one or two lines of text, and we are expecting the system to really understand it. But we all are big users, our students are big users, but none of us really understand what really goes back in the background. How is our data? How is the prompt? I mean, simple piece of text which we are giving, how is it being converted into how is the machine interpreting this text query which we are giving, and how is this query being converted into a model or into a format which the machine understands? How is it retrieving the data from 1 trillion documents? This is when we are talking about ChatGPT-4, we are saying it has been trained on 1 trillion parameters. So on 1 trillion parameters, it has been trained on. So how does this simple query which we give go on to 1 trillion parameters database? And is it a relational database? No, it's obviously not a relational database. The AI world is totally different from your software world. That's one thing we need to be very clear to our students. We need to be very clearly telling them that learning AI is totally different from learning software engineering. So software engineering and AI are totally two different disciplines because we don't think in terms of the way we normally look at software engineering. This is a totally new world, and the way we think has to also change. So we cannot tell our students that this is a normal database, because it's not a normal database. ChatGPT is not having a database just like your Google has. So what does Google do? Google only works on algorithms, and these algorithms better go and search in its databases where all these links have been indexed. The bots have captured every text, the keywords, the tags, and that's how it is being storing. I mean, so when we put in any query in a Google search box, it goes and searches based on those keywords and tags and gets us the results. That's what Google does, and it keeps on bettering it over the years. So you'll be using better algorithms as the time goes on. But when you come to AI, the biggest difference here is we don't go and search in databases, because honestly, none of these databases and none of the books which we have uploaded, I mean 1 trillion books, 1 trillion data content, none of it has been uploaded into relational databases. So this is a big distinction which we need to make to our students when we teach them transformers. So transformers, we need to understand that number one point, we need to understand how data is being stored. If I have to teach transformers, I have to start from the basics, and the basics is how does actually our query get converted into a format is the machine understands. See, machine only understands 0 and 1s, right? So if machine understands only 0 and 1s, how is the text being converted? So let's first understand how in AI, how is the text being input. So what we'll do, we'll start with one basic thing. So I'll go for one or two basic things, and it's an hands-on activities. So I want you to also do these hands-on activities so that we'll understand how our input queries actually get converted in the machine format. So the first part, before starting on transformers, let me start with actually how our query gets understood by a machine. So let's start with that. So we are going to go to tokenizer, and then I'll put this link on. So this is the tokenizer link and meeting ID. So where is this text window? Yeah, chat. So I'm pasting it here. I request you to please go to this link, the tokenizer. This is the first part which everyone needs to understand, how ChatGPT actually understands what you are inputting. So now if you're inputting some text here, say I am teaching ChatGPT to every faculty member here. This is a good course which is ongoing and being conducted by Sri Nageshwar and team at Arya. So now this is what I have given. Kindly understand the distinction between your traditional models and the way sentence splitting happens in AI. So these colors changes which you are looking at the bottom, you can very clearly see that the way we look at token words is different from the way we look at tokens. See, tokens can be meaningful notation of words which is only say 4 letters or 5 letters, or it can be complete words where the meaning is very much clear. So here if you look at Chat GPT, I am teaching Chat GPT, chat is being taken as one word and GPT has been taken as one word. And the same thing, every even though it's 5 letters, it's still one. Teaching, even though it is 7 letters, it's still one. So all of this have been done one, but if you look at here, dot has been taken as a separate token. So this is how tokens are normally taken as. So this is how actually the input goes. And in fact, it's very clear that the input doesn't go even in this format. So let me show you the format in which the input goes. If you look at the token IDs here, so this is exactly how the tokens get captured in the system first. So there are numbers, and these numbers somewhere will be repeated. So wherever there is a duplication, those numbers will be repeated. So in this case, I think we don't have duplications out here, so there's not much repetition out here. So it's all unique text. And this is one thing you need to understand. This is the first step. The first step in your query is to convert it into tokens. That's how the machine first learns. And once this machine has converted into tokens, the second step, what you need to do is how is sentence splitting. So, and sentence splitting again is a big field. I'll not go into deep into it, but I'll just show one small demo of it because sentence splitting itself is going to take, the NLP is going to take a lot of time. So I'll not go deep into it, but only 2 minutes. I'll show you one example of sentence splitting. So what we'll do here is we'll do stemming model. Again, I'll put it here. So I'll just show stemming model, which is a popular, a sentence splitting technique. So we'll go for the stemming model. Okay, let us do Lancaster. Now, if I say here, stemming is for, okay, and let me use the same sentence which I've used here in tokenizer. So once tokenization is done, this is what the machine does. Let's see this. So now when we do stemming, if you can very clearly see, stemming is a process where we take out the suffixes and prefixes out of every sentence, and this is what the machine really learns. See, the machine doesn't input all the data which you give. So if you're just uploading a book of 300 pages, the machine is not going to learn every word that is there in those 300 pages. The machine is going to split every single sentence into it down to its basic essence through all the sentence splitting techniques which we have. So we have around 30 sentence splitting techniques, and that's what we do normally after the tokenization part. So here, if you look at for am teaching, so you're getting only am teach. So ing is gone here. To every faculty, if you look at here, every faculty. So it is going down to the root base. We are looking at the suffixes and prefixes gone, and the root base is what is being captured. So this is stemming. And there's also, apart from stemming, there's also lemmatization also here. So let's look at, we have whether a lemmatization demo in this site. We don't have a lemmatization demo, unfortunately. Okay, we have a WordNet lematizer. So let's do that. So this doesn't work. So we need a lematizer separately. Yeah, some other day I'll just show you lemmatization. So this is one way we do sentence splitting. And these are NLP demos, which you normally teach when we teach NLP. So this is one part. I'm showing you only one technique about how the words are split. And once sentence splitting is done, we go for embedding. So I need to go through all this process, because even if I start transformers and I directly start teaching about transformers architecture, again the questions come, what is this, what is that, and what is embedding. So let me, that's the reason I'm starting with this, so that the questions do not come later. So this is transformers. So we need to understand all this. So if I have to talk about if I have to talk all these things, I have to go for to explain each of these, and that's what exactly I'm doing. So I'm trying to tell how exactly the machine takes inputs, and then how the embedding is done, how the sentence splitting is done. So we'll come to this later, the technical part. Let's look at still the basic definitions, which can be understood by anyone. And that's what we are trying to do. We are trying to make it very simple for everyone to understand, even the non-CSC departments to understand. So this is the NLP part. The first step, you have done tokenization. The second step, you have done sentence splitting. The third step, you need to embed it. So embedding captures the context as well as it doesn't capture just only the, see, normal relational databases, what we do, we only capture words, we only capture the relevance of words or keywords. But in AI, the self-attention mechanism, the beauty part of AI, and the only reason why you are getting split output with just a small text is because when we store data in the vector databases, we not just store the data, but we also store the context of the data. See, till transformers architecture came through, we never had a way to capture the context. But once transformers architecture came through, we were able to capture the context of the words in which the word is being represented in a sentence. So this is exactly what we're going to do. So the third part is looking at the context part. So again, for this, I'm going to take you through word to vectors. Word to vectors is one of the popular embedding techniques. Embedding techniques, again, word to vector has got two methods. One is the complete bag of words and the skip grams. And I'll go to both of them. but I'll just show you the difference between both of them right here instead of going to the technical part definitions of what each of them mean. So that's going to take a long time. So I'll just go through it very simply here. Okay, I need to copy this link. Let me go back to the chat window. And I want you to go log in here. So go to vector demo. You don't need to do any logins here. Again, just copy the same sentence which you have kept in Python. I mean, in the NLP demo, I'm doing the same thing. So now here there are two techniques here. One is CBOW and skipgram. So let me give you a basic definition, very basic definition of what skipgram means and what CBOW means. And for that, again, obviously, I need to go back to okay. I'll just go with one slide so that it is very clear for you. I'll go for the entire thing. Yes. So this is continuous bag of words model in NLP. This is vector wedding. I mean, word to vector has got two techniques. One is this CBOW and second is skipgram. At this moment, it's not important for you to learn everything in depth. Just the basic definition part is enough for you to understand. So in CBOW, the way we look at the target word, so we look at the target word and we get the target word based on the context words. So in this case, the context words are today is a and day, and then that's how we predict the target word in continuous bag of words model. So this is what we use for text classification and language translation. That's how we find every single word is found based on the contextual words. So that is continuous bag of words, and the reverse of it is skipgrams. In skipgram, what happens is, let me show you one simple example. So what happens here, the skipgram, we have a target word and we'll generate the contextual word. So we have a target word called sat and we'll generate the contextual words, which is the cat on the mat. So this is a complete opposite of complete CBOW. So these are the two main embedding techniques, both of which capture the contextual part. So this is the basic definition. I'm not going deep into this because we are running short of time. And let me go back here. So since I've given the basic definition, so the second part is where you need to, okay, is everyone here? I do hope everyone is here on this page. I hope I'm not running very fast. I want everyone to come to this page. The page URL is in the chat window. Is everyone here? Can someone type yes so that, yes, we are, great. So since you are here, I'm just paste the same line which I have done here. And first, I'm going to demonstrate complete bag of words model, CBOW. So CBOW, let me put a window size of 2, just to be very clear. So window size of 2 instead of 3, which is the default which has been given to you. And now I need to generate the data set. So here you can look at it. When I say generate data set, the first thing is what you have already seen in the tokenizer. These are the tokens. So how many letters are there, words are there? You will get the exact number of words. 26 because there's no other grammatical periods on. So you've got around 26 here. Okay, there's a period. So there are 26 tokens out here. And now when you talk about CBOW, as I said, the basic definition is you try to get the target word based on the contextual words, and the window size which I've given here is 2. So now if I'm looking at I, for me, the window size here is am teaching will also get captured along with I data set. So am teaching will also have an output of I, because here we look at the contextual words and the contextual words need to determine the target word. So for the first word, to predict the first word, we are going to capture am teaching as the input. Now, when I look at the second word, which is am, the window size is 2. So on the left side, there's only one word. So I teaching ChatGPT will be the contextual words. Now, if I'm looking at third one, which is teaching, so there is 2. I am ChatGPT 2. And this is exactly I am ChatGPT 2, which is the contextual words for the target word, which is teaching. So the number of training examples obviously are going to be around something similar to the number of token examples. That's around 28. Instead of 26, there will be 28 out there. So this is exactly what CBOW means. So this is complete bag of words where we try to predict the next word based on the contextual words. So once we have done this, I want you to click on randomize. Once you have done that, I want you to train the model. So we are going to train the model on the data set which we have now ended. So let's train the model. So I want everyone to please train the model. And once you have trained the model, I want you to click on run. So we have done this. Since the window size is 2, we are seeing a very close by this is how data is actually captured. So even if you give 300 pages or 1000 pages, this is a 3D dimensional view of how exactly data is stored in the embedding vector databases. This is exactly a visual representation of a vector database. This is exactly how we do the embeddings. And this is how exactly data goes inside the vector database. So only for after this step, we assign an index key, and that's how we do this part. This is how a vector database is built. So this very clearly tells you that this is not software engineering. Software engineering, we input data into, say, even if you're doing some analysis or NLP on that, we'll just keep on splitting the words and we just capture the words. But here, for the first time, we are not just capturing the words, we're also capturing the context of the words. So this is here, this is how it's going on, this is how it is done. Now, if I do the same thing with a window size of, say, 3, you'll obviously have same tokens and same training examples, but when you train the model and you run the TSC, the distance obviously is going to be much more. So this is CBOW. And the next embedding technique which I spoke about is skipgrams. So let me also do skipgram. The same thing, obviously skipgrams, kindly remember what I spoke about the definition. The definition is it tries to generate the context words based on the target word. So obviously your data set is much more going to be bigger. It will not be like CBOW, your data set will be much more, right? So the tokens will be the same, but the data set will be more. So let's look at that. Let's generate a data set. So exactly as I said, the training examples are 156. Now let me show you one. So if I have to determine this is the my word. Okay, let me go to the first word. The first word is I, and the window size is 3. So when I say window size is 3, if you look at the definition of skipgram, which I just said, the skipgram is finding the contextual word with an input of a target word. So for me, the data set which I capture or am teaching ChatGPT, that will be the data set. So for I, if you look at here, what's being captured, I am teaching ChatGPT. If I look at next, say teaching, am I and ChatGPT to every, that should be what it should be covered. So here, if you look at teaching, I am ChatGPT to every. So this is how exactly the data set increases to 156. Okay. So compared to CBOW, because it's a reverse, you're trying to generate the contextual words based on the target word. So this is how you now train the model. We can look at how the vector databases are much different in skipgrams compared to this. So this is when we are running. So this is the way the vector databases are represented. This is how the embedding is done. So this is the two things which we have done. So we have done both, and you also have seen this. So you also understand how exactly word to vector is being done, how the vectors are being created. So the vector databases is the step where we are creating the embeddings, and this is how data is being stored. So your 1 trillion documents which have come to ChatGPT have been stored in similar vector databases on the cloud. And now whenever you give an input to query, so you are asking, say, write an article or write an, in ChatGPT window, you are giving a query. So how does this your query gets converted? Now, this is exactly what I'm going to show, and this is exactly where I introduce the transformers architecture. So let me go back to my slides. Since you have done some demo here, let me close these windows so that I don't get confused. So we are done word to vector, we are done tokenization. So we are back here. Okay. So now we are back here to transformers. So let me come to the basic definition of transformers. So transformers is an attention mechanism, uses an attention mechanism that base the influence of different parts of the input data differently. So this model doesn't use sequence aligned data, which is what we have been using before transformers. I'll come to that. So this is the technical definition of a transformers. I don't want to go into it because I know there are a lot of non-CSC faculty out here as well. So let me directly go into the basic definition. So what we have seen just now, the language modeling history, we see that 2013 we got word to vectors, and then we had RNNs and LSTMs, and only in 2015 we got the attention mechanism. But attention mechanism, though it was available to us an attention mechanism right from 2015, we had its a little bit failings. I'll explain some of those failings. And these failings were corrected in attention is all you need, which came in 2017. So attention mechanism in 2015 came to us, Badnov and others, they brought us the attention mechanism. So we had all these developments happening on, but the self-attention mechanism, which came to us from 2017's attention is all you need white paper, where the transformers architecture was introduced. That's when we started developing a better way of processing huge amounts of data. See, till then, one thing we need to be very clear to our students, we had no way of processing huge amounts of data. Thanks to attention is all you need white paper, we finally found a solution in 2017 when we got this white paper from Google DeepMind. So now transformers architecture gave us a self-attention mechanism which allowed us to look at the important parts of a sentence and capture the context along with it. See, for example, before 2017, if you have bank and river bank versus bank in bank robber, all of the ways same vector representations. So all of them mean the same. So obviously these are the ways which you cannot take AI results because the context varies in all three of them. Bank is a bank, river bank is a bank, bank robber, three different things, but vector representation will be same before transformers. But after transformers, as we have seen just now in skipgram and CBOW, we captured the context, and because of the context, the meaning is better captured. So this is 2017 when all this started. So attention mechanism, by definition, it's a machine learning technique that directs deep learning models to prioritize to attend to the most relevant parts of input data. So innovations in attention mechanism has enabled us the transformer architecture, which is what we have been telling just now. So attention mechanism, as I said, where they came to us in 2014, Badano introduced it because we had shortcomings in RNNs for machine translation. And some research later allowed us to use attention mechanism to CNNs, but again, that was local. So obviously, we use those mechanisms for tasks such as image capturing and visual question answering. But 2017, we started finally to get a way where we can avoid both the sequential say model of RNNs and the convolutional models altogether in favor of only attention layers and standard feed forward layers. So if you talk about the best part of what attention all you need gave us, I would just say two things. So one is obviously the self-attention mechanism, the second is the positional encoding, third is feed-forward network. So I'll explain each of these three because these three are the most important elements which everyone needs to understand, and we need to teach our students as well. And I need to teach you so that in a simpler way, so that you can students can also understand that, and that's what I'm trying to do. So in the industries which where we use this, obviously in all language translation areas or wherever language is used, we use them. We use them also in computer vision because diffusion models are using it for image generation, and also vision transformers are already there. They have achieved very good results for object detection, image segmentation, visual question answering. So there are areas which have got enabled or got created after transformers architecture came into being. Sorry, came into being in 2017. So what is the comparison between CNNs and RNNs? So we already had, as I said, CNNs were there and RNNs were there. So let me explain very clearly so that this question doesn't arise again. So transformers architecture, they have achieved very deep meaning for us. And why they are superior over the other sequential models? See, as I said, we had sequential models earlier. Let me start with RNNs. So RNNs use it to process sequential data. That means they process each time step in a sequence individually in a specific order. So now what happens thus is, so if an RNN is looking at words, okay, it will capture one word, it doesn't capture the dependency. So now the same word might be repeated somewhere else, or the context of this one word might be somewhere in the sentence. But in a sequential analysis, what happens is this word doesn't capture the context of this particular word. So for example, the cat sat on the mat. Only the cat is captured, the mat is not captured. So this is the one difference which you have in sequential analysis. Sequential analysis will not capture the context of those particular words. And without context, there is no meaning attached. So the second part, flexibility over space. So that was time. Sequential analysis is time, and that's why RNNs are very much used in algorithmic trading. I think most of you know that nearly 50% of today's stock trading is being done by algorithms, and that's thanks to the RNNs. And now someone says that we are going to move very soon to 95% of algorithmic trading being done by machines. So that means the entire stock trading already 50% is being done by machines. So 90%, 90 to 95% of trading is going to be done by machines in a year from now. We are not looking very far. We are looking at only 2026. If in 2026, the entire stock market, we don't have anyone spending their time or looking on your mobiles for how much data is there, whether I should buy or sell. You don't need to do that. Let the machines do the job. Let the machines take the biggest mental burden of having to make a decision on whether to buy or sell. The machine is going to look at data analysis, various steps which RNNs are enabling via this algorithmic trading, and we don't need to use them. And AI has obviously helped a lot, and transformers architecture really helps us because attention mechanism allows us to examine an entire sequence simultaneously. Then we had CNNs. So now CNNs are obviously local because we use convolutions. So those faculty, you know CNNs, you know that because we use, when we look at CNNs, we always look at smaller subset. When we pass the windows, the CNN matrix is run through. So when we look at subsets of input data, one piece at a time, we obviously cannot capture the dependency of one segment on the other. So because we are looking at matrix of 2 by 2 or 3 by 3 matrix in a CNN. So that's very difficult for a CNN to discern the dependencies that are very far apart. And that's one reason even CNNs were not possibly helpful for us to do processing of huge amount of text. So attention mechanism obviously doesn't have this limitation for us. So the third one which we had was LSTM. So we also went beyond LSTMs, and that's exactly what I'll explain why we were doing it. So let me come back here with very basic definition so that everyone can understand. So transformers as like a wise village elder. So this village elder who's sitting there, who's listening to everyone. So everyone is talking and everyone is telling something. So the village builder is listening to everyone. He's taking everyone's inputs. But what he listens to everyone's perspectives and he makes a decision that takes into account all viewpoints, no matter how far they think. So if this person is talking about one aspect and this person diagonally is oppositing, providing a different perspective on the same context, and if this person and this person's contexts are totally diagonally opposite, still the village elder is listening to it. And the village elder is capturing all these perspectives and making his decision based on all these perspectives. He only looks at what is relevant, what is most important, what's the second relevant, what's the third relevant. He's going to take these inputs and only look at, so this is about the highest attention weight, this is second attention weight, third attention weight, and these three are what he's going to consider. He's going to let go of the rest. That's exactly a very easy analogy of a transformer. And if you look at how the CNNs work, the CNNs specialize only in creating, say, in this example, if you look at those parts, so we are doing it input by input. We are doing only small parts at a time. So we are looking at local features. We are doing the small piece of fabric one. We are stitching here, then moving on to stitching the other parts. So in the same way, CNNs are very useful, definitely for recognizing objects, but piece at a time, but patterns, edges, textures, spaces, but it cannot capture the dependencies in images as well. So CNNs fail there. Now let's look at RNNs. So RNNs, let's look at a storyteller, for example, a storyteller who's telling stories. In these stories, the way it's done, so RNNs are good in like just like a gossip chain. See, an example in a gossip chain, one person says someone has died. The second person says someone has died because of say some disease. The third person says he has died because of disease, and the third person was taking treatment for so and so. By the time this gossip chain runs around 10 people, from one single line, he died, it becomes he died because he had a disease, he went to this hospital, he has so many relatives, he has got so many friends, gossip chain. That's exactly how RNN builds on. Stories are passed on from one generation to another, and these storytellers remember the previous story, the context of the previous stories to tell the next story. And that's exactly how algorithmic trading works even in the stock market. The stock market, if one has to take a decision, if the machine has to take a decision, it takes into context the past information. How the stock has moved, RSIs, how the volume has increased, purchasing capacity. So how much shares have been purchased, the volumes, and or relative stock index, RSIs, the technical indicators, the Bollinger Bands, the 20-day window, the 50-day window, the 200-day window. All these technical indicators together, the data is being captured by the machine and it's able to process that machine and doing that. That's exactly where the RNN really helps. So RNN is good at sequential data where the memory of the past inputs influences the current output as well. So this is RNN. So you can understand very clearly why this is not useful for us in processing huge amounts of data. The fourth part, long LSTMs. So LSTMs, short-term memories, which came to us after RNNs didn't fulfill processing of data text part. So now what the typical analogy here is, say our LSTM is like just like a history keeper in a library. So history keeper in a library, he knows which memories to keep and which memories to discard. So he knows what are irrelevant or what are not relevant. So he prevents the loss of important information, but at the same time he discards whatever is irrelevant. And this is exactly the next step, the transformers, where we to get only the most important part and discard the irrelevant part. So these are the shortcomings which we had. So RNN's shortcomings were there, and we had the LSTM shortcomings. So no RNNs, we had this problem because it limits the greatly limits the length of input sentences because it doesn't capture the context of one word, even if it's repeated in the second or maybe eighth or ninth word in a sentence. So RNNs had this problem. And then these problems were overcome by LSTMs, as I said. So LSTM applied some gating mechanism, but still it was not sufficient. Then we had sequential to sequential. So this was the method which we introduced to overcome the more problems of LSTMs. So LSTMs, what it did, it used two LSTMs. The first LSTM was the encoder, second one is the decoder. Even here, what has happened is we were able to look at hidden state, but we are only looking at only one hidden state, not multiple hidden states. So that was one problem we had. Even this. So Baudano again proposed an attention mechanism for us in 2014. So instead of passing only the final hidden state, which was a contextual vector, the model passed every encoder hidden state to the decoder. So this was some improvement which we did in attention mechanism, but still it was not sufficient because we wanted to pass all hidden states, and that's exactly where it came from. Attention is all you need. So this is exactly what came down to us at self-attention mechanism. So for example, in RNS, Jane went looking for Jack is obviously different from Jack went looking for Jane. So RNS will not be able to do this distinction here. So now transformers, obviously a super smart translator, as I said, you can also take an example of a parrot. See, parrot listens to us, parrot listens to everything that we say, but it doesn't repeat or parrot something. It remembers only one or two sentences or one or two words. It keeps repeating those sentences. So just like that, the parrot only repeats some of the important sentences. So what is most important aspects in transformers? So transformers, things to remember is positional encoding, attention, and self-attention mechanism. So these are the ones we need to done. So if you take this one simple example, J Suis etudiant, we need to do a sentence translation into English. So now what we have to do, we have seen this. First thing is tokenization, second thing is embedding. And after the embedding, then it passes on to the encoding part. The encoder has got a self-attention mechanism and a feed-forward network. And this output goes to a decoding component, which has got an attention mechanism in between the self-attention and feed-forward. And that's how this positional encoding is. After the positional encoding of the decoder, we get the final output. And if you look at the final output, this is a translation of this particular word, which is I am a student. So now this is what we look at. I'll be not be going into too much into deep details because we need have an exercise also to be done. So what I would just like to show, is show the architecture part of the encoder and the decoder, and move on to how this is exactly done. So in 2 minutes, I'll just complete this part and I'll go to an exercise. So what happens is, so this is your J Suis etudiant. Now it's getting converted into tokens, and after tokens, it's getting converted into embeddings. And after embedding, we send it to the encoder. So encoder now is passing through the self-attention mechanism. So once after the embedding is done, each of the embedding vectors flows through the two layers of the encoder. The first one is the self-attention mechanism. And after the self-attention mechanism, it passes through a feed-forward network. And once the feed-forward network, it gets passed, so what happens exactly in the self-attention layer? So in the self-attention layer, we break down the input embedding into three vectors. So one is the query vector, the key vector, and the value vector. And for these vectors, then are computed using weights that the transformer learns during the training process. So all of these computations happen in parallel. So once we have the query vector and the key query key and the value vectors, what we do, we multiply each of these value vectors with a softmax score. Now, what's a softmax score? So now let us look at the softmax score. So this is softmax score. We multiply it so that we want to keep intact the values of the words, leaving out irrelevant words. So this is exactly what it's done. So the intention here is to keep intact the values of the words which you want to focus. So this is exactly a summarization of what exactly happens. We input natural language sentences, we embed each word, we perform multi-headed attention and multiple embedding words with the respective weight matrices, we calculate the attention, and finally we concatenate the matrices to produce the output matrix, which is the same dimension as a final matrix. And this is basically the technical part of transformers, which you don't need to go into depth. It takes a lot of time, but it's just the basic definition which I want you to teach. So we have these transformer models. The types of transformer models we had is encoder and decoder. We had BART, and all the ones which we are working today are decoder models. The GPT-3s, the GPT-2s, there's all our decoder models. And the encoder model is BERT, which is one of the first models which came after the transformers architecture came. And most of us use BERT today because BERT is easy to use and you can always download it onto your desktop as well. And that's why most of us use BERT for fine tuning or for our tasks. So BERT is trained in both variations and is able to handle very long input content as well. Now what is going to do? So this is enough for now. What I want you to do, I want you to be rewarded for what you have learned so far. So now let us go here. Let me post it.
Sir, presentation is not visible. You can switch. Presentation is just to bring to your notice.
Just a minute. Can't share content, sir. It says you can't share contents unless the host makes you the presenter. Sir, you need to make me a presenter. It has gone. It says you can't share context unless the host makes you the presenter.
Sir, you forward the presentation to host, he will share, I think. Otherwise, you can share directly.
No, sir, still not here.
I'm sharing, sir. Just 1 minute. Give me 1 minute.
Sure, sir.
Your name is not visible in the participant. That's why I'm checking, cross-checking. Now it is visible. I will give. Now okay, sir.
Okay, sir. So now if everyone comes here, let's do a small batch. So if everyone comes here, can everyone come here?
Yes, sir.
So all I need you to do is to drag these videos which are here. There are 4 videos. Please drag these videos. You don't need to look at them, just drag them and click on next. Same thing. You don't need to look at this, click on next. You will come here. So everyone has come. Is everyone here?
Yes, sir.
Sir says, Vinod Kumar sir says, tell again. So let me tell again, sir. Sir, you go to this course, first video. You don't need to watch the video. Please drag it here. And let it close. Click on next. The same thing you do even for the second video. Click on next. And you'll come here, sir. Please come to the quiz. So is everyone here at the quiz? Is everyone here at the quiz? Okay, fine. So if everyone is here, so let's go to the quiz. Transformer model. So this is exactly what we have learned now. It's a deep learning model that uses self-attention to learn between relations between 2 different parts of a sequence. So this is one. Second question, what are the encoder and decoder components of a transformer model? So what it does, for example, here, The encoder ingests an input sequence and produces sequence of hidden states. The decoder takes in the hidden states. So as I said, in LSTMs or the other earlier versions which we had sequence to sequence, we had a problem. Even in RNS, we had a problem because we got only one hidden state. But in transformer architecture, we were able to get all the hidden states. So that's exactly what the encoder gets. Encoder ingests an input sequence and produces a sequence of hidden states. And the decoder takes in all the hidden states from the encoder and produces an output sequence. That's exactly what we see here. So these are all the hidden states. So you can look at these, all these hidden states. All of them are available to us. And we take all these the hidden states, apply the attention weights, and then only we provide the output. So this is the answer. The encoder ingests an input sequence and produces sequence hidden state. So what are the two sublayers of each encoder? That's exactly what we have seen. Self-attention and feed-forward. What does fine-tuning a BERT model mean? So we do fine-tuning of a BERT model when we want to train the model on a specific task where, we want to add more their domain-specific data. And we need to update, obviously, the pre-trained weights. So that's exactly what we'll do. We'll train the model. We update the pre-trained models on a specific task by using label data. So what is the attention mechanism? It's a mechanism for determining the importance of each word in a sentence for the translation of another sentence, a way of determining. So obviously, answer is 2. What kind of transformer model is BERT? We have just seen that it's an encoder only model. That's exactly what we have seen here in the slide. BERT is only an encoder only model. Okay. So BERT is a transformer which was developed by Google in 2018. What is BERT used for? So it is used to solve many NLP tasks, question answering, test classification, and NLP interference. And now what are the 3 different embeddings that are generated from an input sequence in a transformer model? That's exactly what we have done. The 3 different embeddings which are coming to us. So that's now let's look at what is the name of the language modeling techniques that's used in BERT. So that's exactly what we have said, transformer. Now I just want you to click submit. Done. 100%. Your passing score is 75%. Fine. Done. Click on next. Lab. Okay. What I want you to do is just open the lab and then close it. If you want, you can run it, classifying text, but you need to sign in here. You need to sign in for this. Again, you need to sign in. So for now, just close it. And you are done. You have completed your transformers module and you get your badge. This badge will be available in your login. You can put it on your LinkedIn. So you have completed transformers model and BERT model. So congratulations, you have completed one advanced GenAI path from Google today. So that's the transformers path which you have done exactly. So another thing what I want you to do is the attention mechanism. Since we have spoken about it, I want you to close even this today. Again, I'll put the link. Please log into this attention mechanism and start the module. Now this is exactly what I was talking to you. Attention model has got several hidden states and the several hidden states get passed to the decoders, and the decoder takes these hidden states along with their weights, and that's how the next stage starts. In all other earlier models, we had only one hidden state, but in attention model, we pass on several hidden states. And that's how the final decoding part comes. I am a student, that comes up. So attention model obviously differs from a traditional model. It takes more data, it processes more data, it focuses on the most relevant parts, which is the encoder and the decoder, and it looks at the set of the encoder hidden state which it receives. And gives each hidden state a score, and then applies a softmax multiplication. And finally, once the softmax multiplication score is done, the translation happens here. So these are all the hidden states, several layers. So black cat ate the mouse gets translated finally into this. So this is the attention mechanism. So you can click it next. Not over. I still don't have a green tick. I need a green tick here. Okay, next activity. So what is the purpose of the attention weights? That's what we have exactly done. Right now we have learned it. We are assigning weights to different parts of the input sequence, with the most important parts receiving the highest weights. So what is the advantage of using attention mechanism over a traditional RNN? So attention mechanism, that's what exactly what we have seen here. Why we don't use an RNN? RNN processes sequentially, but it doesn't capture the context. So I think this is very much evident. You will all obviously be doing much faster than me. Attention mechanism lets the decoder focus on specific parts of the input sequence. And what is the name of the machine learning architecture that can be used to translate text from one language to another? I think you can do it very easily this. What is the name of the machine learning technique that allows a neural network to focus on specific parts? That's exactly what we have done now. What is the advantage of using the attention mechanism over a traditional sequence mechanism? So that's exactly what we have learned. It allows us to focus on specific parts of the input sequence. And how does it differ from a traditional model? So traditional model, attention part models obviously pass a lot more information to the decoder. So what are the two main steps? What do? That's what we have done. We calculate the attention weights, we generate the context vector. Or we calculate the context vector and generate the attention weights. Calculate the context vector and generate the output word. So what do we do actually? What we do? We generate the attention weights. So we calculate the context vector and we can generate the attention weights. So that's exactly what we do. Now let us look at submit. Okay, we have passed even this. We have done this. So click on next. You have done this. So you have got 2 badges today. So all of you have got 2 badges today. You can happily place on your LinkedIn these badges. So you have completed both the attention mechanism and transformers architecture. This is advanced GenAI in Google Cloud. So you have done both. You have done attention mechanism and you have also done transform model. So congratulations for that. So you have completed both of them. Yeah, so we are not doing other ones. So these are the 2 which are relevant for us. Now, so this is the technical part of it. Now let me try to do this much more easier way for you. About 10 more minutes, so I'll tell a story. I'll tell a story which makes it much more easier for you to understand how this can be taught much more easier. So these are stories which we can use So this is exactly the transformer architecture. It shows the encoder and decoder, highlighting the key components such as the self-attention layer, the feed-forward networks, and encoder, the multiple encoders, decoders. So what I've done to make this simpler, I use normally stories, and some of these stories are what I'm going to teach you also to learn and do it while you are teaching students. So a simple story, I created a small story in which there is a wizard. This wizard gets a book called Transformer, and he wants to generate new stories using this particular book called Transformer. So for that, he has to create 4 different types of creatures, and that's exactly what he does. And these are the new creatures which came to us via the transformer architecture in 2017. Attention is all you need. So let me introduce to you, gentlemen and ladies and gentlemen, the 4 creatures that came to us via that white paper. So this is the magic word, kingdom of magic words, and the book called Transformers. So what did we get exactly? Attention is all you need. So first thing, what we showed you was the embedding part. You say if you have got 1 trillion parameters, 1 trillion books, all these books have been embedded. Every single word in these books has been embedded into a meaningful help. So that's what we have seen. We have shown you CBOW, we have shown you skipgram, we have shown you how we capture the context of every single word. So it's not just one word, we capture the essence of the entire word, and that's exactly what the embedding else do. The embedding else take every single word from the kingdom of words, they transform it into a unique magical rune that holds the essence and meaning of the word. So that's the first part, the embedding else. So now these attention fairies, these are the new creatures which we have created. So self-attention mechanism brought on to the attention fairies. So what do these attention fairies, what are they important about, and what is their importance that makes them so powerful, and what is their relevance that allows us to claim them as a harbingers of this new revolution in AI? This is because attention fairies have the incredible ability to focus on the most important part of any story. So they can look at a sentence and decide which words are important, while at the same time discarding the rest of the words. So that's exactly what the attention fairies did. And once it has been done, now it requires a much more powerful creature, and that's exactly what the feed-forward networks does. So for the feed-forward network, I had to search for analogies. I worked a lot on this. Then I went for Ravan. Ravan with his 10 heads, he was more appropriate to me because in feed-forward, everything works in parallel. And I wanted to show my students how it is possible for a machine to be doing all this process in parallel. We have got multiple attention heads, multiple hidden states, all working in parallel. So how is it being done? That's why I used the analogy of Ravan with his 10 heads, and I created this multi-headed dragon. So this multi-headed dragon was created by me to explain to my students and faculties from other branches how these dragons have these multiple heads, each capable of looking at different parts of a sentence simultaneously. So they work together to understand the context and relationship between words, making sure that the story flows smoothly. So the feed-forward networks are what are the multi-headed dragons. So they have got multiple attention weights, multiple hidden states, not single hidden state. And these multiple hidden states have got attention weights. They are again multiplied with the softmax score, and those weights are passed on, and obviously the words with the highest weight may be close to 1. See, the weights are obviously from 0 to 1, and the weights which are very close to 1 are obviously the ones which have got the closest similarity, and the weights which are close to 0 are the ones which are very far away from each other. So these are the multi-headed dragons. And then once we have this information, So we have this query here, which is being done by one of us. We are putting a query, write me an article on, say, generative artificial intelligence. See, generative artificial intelligence might be present in, say, around 20 lakh articles. Maybe we are talking about 1 trillion. So it's okay. Say around 20 lakh articles are talking about Gen AI. Now, all this information has been captured by ChatGPT in its vector databases. So what happens here is when we put our query, this query gets again converted into a vector. What we have seen, tokenization, embedding gets converted to a vector. So even our query vector goes and searches in this vector database, and where we have got cosine similarity, this vector database tries to find all that. So when I say 20 lakh articles have got mention about Gen AI, so these 20 lakh articles are one where the searching starts. And once this multi-headed dragons and the self-admission mechanism works on these 20 lakh articles and brings it down, say around to 100 pages. On these 100 pages, we again do this iteration. Finally, we come down to capturing the essence of these 100 pages and bring it down pass it on to the ones who are going to make it more relevant. So, and that is where the positional encoding, the most powerful feature of transformers coming to the picture. The positional encoders are the ones which apply a weight to every word that is being captured there. So they apply a number, and the positional encoding is what helps us remember how each word is relevant with other words. So now that is the reason when we have to produce the output. We remember even in the decoder, kindly remember this architecture, even in the decoder, let me put this up. Even in the decoder, we have the same components, the self-attention and the attention mechanism and the feed forward. So even in the decoder, we have these elements which position the data in a format which is, see, one thing you very clearly agree, ChatGPT has got impeccable grammar, beautiful way of presentation, and all this is possible because we created an entire new creature called positional pixies. So that's the name which I have given to them. This is my imagination running wild. So these positional pixies are responsible for understanding the order in which words are appearing, and they use their magic to ensure that sequence of words makes sense. So this positional encoding is exactly what happens when the data is captured, and this positional encoding is responsible for putting the words in a sequence, the grammatical flow, the sentence flow, the paragraph flow. It is a responsibility of the positional encodings to ensure that this is done and then send it to the output vector, output database, that's a decoder. And the decoders finally present the output to you, which you are seeing every single day. Teachers, faculty members, this is what we need to teach our students, the power of transformers, and we need to teach it in this simple way because it's very hard to teach self-attention mechanism. So we need to teach them in a very simpler way so that they will understand how the transformers actually work. And this is very important for them if they cannot appreciate how ChatGPT has ingested 1 trillion documents and is responding to us, they'll never be able to understand AI. So with that, I conclude my session. I've got 2 more minutes. I started late, so I'm using that liberty, Nagesh Garu. So that's, I'm open to questions.
Any questions from the participants? So I request participants to post their questions in the chat, or they can unmute themselves and ask.
Hello, I couldn't listen.
I have unmuted, sir. They are free to ask any
Okay,
questions
sure,
they
sir.
like.
You can type as well. Anyone has any questions, you can type as well. One thing, the ones who came on Monday for that session on which we had, the GenAI in Academia, I have shared with Nagesh Garu the document which I said I'll be sharing. So the document which contains all the URLs of all the sites which we went to, the tools which we are using. So that has been shared with Nagesh Garu. Nagesh Garu sir will be sharing with all of you. So that's one input I forgot to mention.
So already we posted in Google Drive, sir. All the links and videos will be shared in the WhatsApp group. We have posted. All the days will be available from today. Yesterday also they are available.
Sure, sir.
Any questions from the participants? So if there are no questions, I would like to thank Desu Garu for giving a wonderful lecture. Now
Thank
I
you, sir.
requested Dr. T. Anuradha Madam to propose vote of thanks for this particular session. Over to Anuradha Madam.
Okay, sir. Good evening, everyone. On behalf of all participants, I take this opportunity to extend my heartfelt thanks to our esteemed resource person, Uma Desugaru, for delivering such an enlightening and insightful session on generative AI tools for AI, for academia and research. Your expertise in in-depth knowledge of the subject have given us valuable insights into how generative AI can revolutionize academic and research activities. Your deep dive into the basics of CNN, RNN, LSTM, transformers, and BET models was truly enlightening and provided us with valuable knowledge to navigate the existing field of artificial intelligence. The practical tools and real world applications you shared have not only broadened our understanding but have also inspired us to explore new possibilities in our respective fields. Your ability to connect theoretical aspects with practical examples was truly commendable, and I am confident that everyone here has gained knowledge from your session. On
Thank you,
behalf
ma'am.
of all the participants, I thank you once again for sharing your time, expertise, and experience with us. We are grateful for your valuable contribution to this faculty development program. Thank you so much, sir. And we hope to have the opportunity to learn from you again in the future. Thank you, sir.
Hope so, ma'am. Thank you, everyone, for this opportunity. Thank you, Nagesh Garu, for participating in your ATAL program. And thanks to all participants, all faculty members. I just want to say we are in a very challenging times, and because the rate of technology adoption is going on in a non-linear fashion. I mean, every single